we have a question from mathematical analysis. So we know that the limit of xn minus a over xn plus a is equal to 0 as n approaches infinity. Knowing that, we want to show that the limit of xn is equal to a as n approaches infinity. Now, we're going to prove it by definition. So we want to prove that for any epsilon that's larger than 1, there exists a capital N, so that when little n is larger than capital N, the absolute value of xn minus a is strictly less than epsilon. Now, knowing that this limit is equal to 0, we can say that for any epsilon, some random arbitrary positive number, for this epsilon, like fix this epsilon, then I can derive another positive number. Let's call it epsilon over 4 times absolute value of a. I'll explain later why I come up with this magical number. So, according to the definition, if the limit of this is 0, then for any epsilon, or for any positive, random arbitrary positive number, now I'll use this as my random arbitrary positive number. So for this particular number, I can always have, when there exists a capital N naught, when little n is larger than capital N naught, I can always have absolute value of xn minus a over xn plus a is always strictly less than this particular positive number, epsilon over 4 a absolute value. This is according to the definition of limit. Just for this particular limit, I've already found a capital N naught. Don't worry about the exact numerical value of this capital N naught, as long as we know that it exists. All right. We have this inequality relationship. Now, let's multiply both sides by xn plus a, absolute value. And then we have xn minus a, positive absolute value, is now strictly less than, so multiply the bottom absolute value over here. We have epsilon over 4 a absolute value times absolute value of xn plus a. We have this. Then I can say this is further equal to, right hand side is equal to, let me just write up here, equals, copy down the coefficient here, epsilon over 4 a absolute value of xn, I want to minus a. Of course, I have to plus a to make it the same. Also, I have a plus a here, so I have to plus 2a. So that's still the same thing, right? xn plus a, xn minus a plus 2a, xn plus a, same thing. So it's a common technique in mathematical analysis to subtract a term and to add up the term, same term again, to make it the same thing. So again, we can use triangle inequality and say that this must be less than or equal to, copy it down, coefficient, then the absolute value of this is less than or equal to absolute value of xn minus a plus the absolute value of 2a. That is splitting the absolute value into two absolute values, triangle inequality. So quantity, absolute value of xn minus a plus 2a, absolute value quantity. Okay, expand the bracket now. This distribute to that. We have epsilon over 4a, absolute value times absolute value of xn minus a. Then distribute this onto this. So 2a absolute value, 4a absolute value, simplify down to just 2 at the bottom. Epsilon still at the top. So plus 2 at the bottom, epsilon at the top. We have this inequality. Okay, so remember, we've started from here, and the direction of the inequality remains. So in the end, I can say this absolute value is strictly less than this expression. Now I can realize there is a common factor, absolute value of xn minus a. Absolute value of xn minus a. Move this term over here and factor it out. And then we have still an inequality. Our common factor would now be absolute value of xn minus a. Since we have factored it out, we have a coefficient of just 1. And this coefficient moved over there, so it's minus. So quantity 1 minus this coefficient, epsilon over 4a, absolute value quantity, times the absolute value of this. And I have epsilon over 2 on the right-hand side of the inequality. Okay, eventually I've reached to this inequality. So I'm going to divide this coefficient over here. So before I divide it, I want to make sure that this whole quantity is positive, because if it's negative, then I have to change the direction of the inequality. So how do I make sure that this quantity is actually positive? Of course, I have to impose a restriction on the value of epsilon. Okay. Now I can say I'll just get rid of this. And that. And that. And I don't need this anymore. Okay, because all I need is this expression. Now, how do I make sure this quantity is positive? I can do that by saying that let's restrict epsilon to, of course, greater than 0 and less than 4 times absolute value a. Then I can easily prove that epsilon over 4 times absolute value of a is strictly, it's easy for me to prove that epsilon over 4 times absolute value of a now is strictly less than 1, larger than 0. Just easily on this inequality, divide epsilon by 4 absolute value of a, and divide this term by 4 absolute value of a, simplify down to 1. So we have a 1 here, and then we also have 0 here. So therefore, then I can further prove that 1 minus this quantity is already in between 0 and 1. So 1 minus a quantity that's in between 0 and 1 is of course positive. So therefore, I can simply divide this term over here and still maintain the direction of the inequality. Now I have xn minus a. Absolute value is strictly less than epsilon over 2. That's on top. Bottom, I have this term. 1 minus epsilon over 4a. Absolute value. I have this inequality. Okay, now I want to further restrict epsilon. I want to further restrict epsilon larger than 0, less than 2a absolute value. That way I can make sure that if I say epsilon over 4a, so this inequality can lead me to, if I divide epsilon by 4a absolute value, divide 2a absolute value by the same thing, 4a absolute value, simplify down to just half, less than half, larger than 0, of course. This is easily proven. Now that will lead to, because I have 1 minus this quantity. This quantity is in between 0 and half. So therefore, 1 minus epsilon over 4a, absolute value. This quantity is in between 0 and half. So 1 minus a quantity that's in between 0 and half should be larger than it's already larger than 0 and also larger than half. We can safely say that. Because when you subtract something that's in between 0 and half from 1, of course, it's always going to be strictly larger than half. For example, if you have 0.2, right? That's in between 0 and 0.5, you have 0.2. So 1 minus 0.2 is 0.8, always larger than 0.5. So this is good. So I can further loosen this inequality and say this is actually less than, copy down epsilon over 2. And the bottom, you replace the bottom with half. So remember, if everything is positive, then the smaller the denominator is, then the bigger than the whole fraction is. So now I've replaced some quantity with half, and the half is smaller now. Half is smaller than this quantity. So the bottom has become smaller. Everything is positive. Bottom has become smaller. So the whole fraction is now larger, right? This is smaller than that, so this is smaller than this, so this is larger than previous, so it's now loosened, it's enlarged. Now, so now I have epsilon over 2 over half. That is epsilon. Okay, so simply speaking, I've reached to the point where absolute value of xn minus a is strictly less than epsilon. Right? When does that happen? Is there any restriction to this small n here? How large must small n be in order for this relation to be true? Of course, when small n is larger than capital N naught, this is my restriction. As long as small n is large enough, then this inequality is always true. So this inequality is in fact this statement, this part of the statement. Right? According to the definition, this is what we want. This is what we want to prove. Given any epsilon, right? We've randomly given any epsilon. Can we find a capital N? Yes, we found indeed capital N naught. It is our capital N, so that for every little n that's larger than capital N naught, this inequality is true. That is, this inequality is true. So according to the definition, we've really found a capital N that satisfies this relation. Okay, so now you see the reason I came up with this magical number, epsilon over 4 times a absolute value, is so that I can successfully cancel out everything in the end and achieve just epsilon. Okay? But alternatively, you can also say, okay, let's just use epsilon straight away instead of this magical number. I mean, in that way, it's also fine. The only difference is that in the end, you may come up with, instead of epsilon, you may come up with four times absolute value of a times epsilon, something like that. And that is kind of okay, but not desirably perfectly enough, because according to our original rigorous definition, we have to achieve something that's exactly epsilon in the end. Right? So, not that perfect, but this is also fine, because remember, epsilon just means very, very small, infinitely small, small enough. So when you multiply an infinitely small amount by 4 times absolute value of a, that is multiplied by a constant, positive constant, and it's still going to be an infinitely small amount. Right? So from that sense, it's also a legitimate proof, even if you achieve something that is not exactly epsilon, but some positive constant times epsilon is also legitimate. Okay? But by doing this, it just, looks more neat and more, desirable, more perfect, more good looking. But either both ways are legitimate. Okay, whether you want to use epsilon straight away or use epsilon attached with some positive coefficients, whatever, both are good. Depending on different kind of questions, sometimes for different question you may come up with some magical number that has something to do with epsilon multiplied by some other coefficients. For example, epsilon over 2, epsilon over 3, something like that. But in the end, you get the idea is the same. You get it. Alternatively, we could also say that maybe I can use substitution, say let yn equal to xn minus a over xn plus a. Then let's solve for xn in terms of yn. So we've again known that this limit is 0, so that yn tends to 0. And so therefore it will be easy for us to determine the limit of xn if we just represent xn in terms of yn. Should be very easy. So, but let me know in the comments, how would you prove this statement using yn substitution?